Welcome to the course on power electronics with wide bandgap devices. This is our second lecture. In this lecture, I am going to discuss about characterization of the wide bandgap devices. So this is in continuation with the previous lecture. So there I have discussed about different types of wide bandgap devices, mainly focused on gallium nitride and silicon carbide, their advantage, challenges, their current trends, and the applications. Also, I have shown datasheets of silicon carbide, gallium nitride, and silicon, and also discussed their comparison. So, as you have seen in the datasheet, so different parameters are actually given. Those are required for designing converter. So, the important parameters I have discussed in the previous lecture. So, if you want to see more parameters, then you can download those datasets from the website. So now if you download the datasets of the same devices which I have shown in the previous lecture, that is silicon carbide and gallium nitride, using same part number, then you will be able to see for silicon device there are like much more information given in the datasheet as compared to silicon carbide and GaN. Similarly, for silicon carbide, comparatively more information is given as compared to GaN, and comparatively less information you will get in the GaN datasheet. So, what is the reason? So, basically, these devices, these wide bandgap devices, are comparatively new. They are not that much mature. So, not all the information related to design are given in the datasheet. Some informations are given which are important, and some they may be important but like they depend on different electrical or thermal condition. So those informations are not given because those are not known. But for designing the converter, those information may become very significant for some of the researchers or the users. That is the reason it is important to characterize these devices. So this is what I am going to discuss in today's lecture. So basically, motivation behind the characterization. So when I say motivation, so then there are few points you need to know. So what are the motivation behind this characterization? So first is that, so the wide bandgap devices such as silicon carbide and GaN they are comparatively new and not matured. So all the informations are not available in the datasheet. So then if we require some information which are not available in the datasheet, then what we have to do? We have to characterize those devices. So basically what we have to do, we need some practical condition for which we will be designing our converter. So the wide bandgap devices need to characterize considering practical conditions. Second is that, so the datasheet is incomplete and not the information is given, all the informations are not given with respect to different electrical conditions. So basically the condition which they have considered for the characterization of the datasheet, that may not be the same condition for which you need different parameters. So then you need different parameters with respect to your electrical conditions. So let's say in the datasheet you must have seen different electrical conditions are given. Electrical conditions means different types of voltage, current, and the temperature. If you remember, I have discussed in the previous class, So with respect to different temperature, current carrying capability of the device changes. Means at 25 degrees Celsius, if the device is capable of carrying 15 amperes current, so if the temperature increase to 100 degrees Celsius, then what happens? Current carrying capability of the device reduced to, let's say, 12.5 amperes. Same thing happens for all the devices. So the reduction may be different, but definitely there will be reduction if the temperature increases. Similarly, if the electrical parameter changes, means the voltage for which we are considering the characteristic. So let's say VDS, if it increased from, let's say, 100 volts to 400 volts, so definitely the capacitances whatever is present, which I have shown in the last class, input capacitance, output capacitance, reverse transfer capacitance, those capacitance values will also change. And same as the with respect to rise time and the fall time. So obviously if those parameter changes, so that is going to affect the converter operation with respect to, let's say, dynamic characteristics, static characteristics, and also to find out losses in the converters. So that is why we need to consider different electrical condition which will be suitable for our application. So suitable electrical conditions for characterization. Similarly, we need to consider suitable thermal conditions as well. Suitable so it may happen the converter which we need to design, that probably will be used for an operation where the temperature will vary from a range of, let's say, 25 to 50 degrees Celsius. So then we have to see, like at room temperature, let's say 25 degrees Celsius is the room temperature. In that condition, what are the values of different parameters? And similarly, for 50 degrees Celsius, what will be the changes in the parameters for that particular device? Then we have to design the converter with respect to that. Now, these are with respect to different conditions. Now, this is not only the only reason why we want to characterize the devices. Also, these devices are suitable for high frequency operation. So the layout design of these devices will be different with respect to the silicon device. Why the design will be different? Because some parameter which may not be significant for silicon device related design, that may become significant for wide bandgap devices due to consideration of the high frequency operation. So then if we are like using these devices, or we are designing one PCB for the characterization, then we have to consider all these points. So in that process, what will happen? We can extend that knowledge for designing the converter using those devices. So basically, layout designed for converter characterization will be beneficial for designing the converter. And another important thing is that whenever there is some new device, so then we need to learn about the device. So what type of device, what are their characterization, how we can use this particular device, where this can be applicable. So this is actually best way to learn a new device, by characterizing the device. So this is best way to learn about any new device. So these are the different motivations for characterizing wide bandgap devices. So now this motivation also exists for silicon devices, because like when silicon devices came in the market, so then that was also new. So probably people have spent lot of time to learn about those devices. So then why we have to reconsider these points again? So basically the difference between silicon and the wide bandgap devices causes to learn about these new devices more challenging than that of the silicon device. So whatever the existing method available for silicon devices to get the characteristics of the silicon, so that may not be suitable directly for wide bandgap devices. So the reason why it will not be suitable is because this device packaging is much different than that of the silicon device. As you have seen in the previous lecture, the GaN packaging is much more different that of the silicon carbide or the silicon devices. So basically those are SMD type of devices, and they are very thin, and also accessing different points, gate, drain, source points of the GaN devices is much more challenging than that of the silicon carbide or silicon devices. So then the existing kind of equipment, whatever is available for characterization of the silicon device, that will not be suitable directly for GaN devices. So then we have to find out different method, or we have to modify the existing method in order to characterize those new devices. So that is one important thing. And second thing is that whenever we are actually characterizing silicon device, so additional wear length may not cause that much problem, because the parasitics for silicon device may not be that significant, what may be very significant for the wide bandgap devices due to high frequency operation. And third thing is that whenever we are going to use any equipment, that equipment may not be suitable to test any particular device, new device, so for high frequency operation. So their frequency may be limited considering the silicon device. So those are the different devices cause us look for new methods or modify the existing methods for the wide bandgap devices. Okay, now I'll tell you about different types of characterization. So what are the characterization you need for your converter design? Basically, what are the different parameter you need with respect to the converter design? So when we say converter design, the first thing which comes to your mind is that rating of the device. So rating of the device means what are the voltage and current ratings. So those are the first thing which we look for a device, like whether that device will be suitable for this much voltage rating and this much current rating. Let's say any device is having voltage rating VDS which is of, let's say, 400 volts, and ID which is of 10 ampere. Okay, so when we try to design any power electronics converter, any converter, buck converter, boost converter, what we see, what is the rating of the device? Rating in the sense there are two parameters, one in term of voltage, another in term of current. So when the device will be off, in that time how much drain to source voltage is appearing across the device, and when the switch is on, what is the drain current maximum will be flowing through the device. So based on that, we can actually select the maximum rating, and then from there we can select the device which will be capable of carrying that much current or can have that much voltage trace across it. So now these two parameters can be find out from the device characterization. So when we say device characterization, for that we need static characterization. So this comes under static characterization. So static characterization means the device is basically reaching to steady state. So when we turn on any device, so initially there will be some time required to reach the device to the steady state. When it is turning on, it will take some time, which I have shown in the previous lecture in terms of rise time and delay time. That time is required to reach the device to steady state till it is carrying the rated current. So in steady state, it will be probably carrying rated current. So that rated current we can get from this static characterization. Similarly, during the turn off condition, when the device is turning off, so that time is also given in the datasheet in terms of delay time and the fall time. So after the delay time and fall time, the device will be completely off and the voltage trace across the device will be in terms of VDS. So this VDS can also be that this information we can get from the static characterization. So what we have to do for this static characterization? So we have to provide a gate pulse. So this gate pulse should have suitable pulse width so that device can reach to steady state. Now this gate pulse is very important. What should be the pulse width of this gate pulse? Because like if we try to keep width of this gate pulse very small, then probably the device will not reach to the steady state. Then we may not have the actual information of the VDS and ID. So then it will be difficult to find out what can be the maximum rating of the device. Now if this length is this width of this gate pulse is much wider, then what will happen? That will cause high conduction loss, because when the gate pulse we are applying, we are expecting device to conduct. So then what will happen? The device will be in conduction state. So in that time what will happen? Due to the device conduction state, there will be conduction loss. So this conduction loss can cause temperature of the device to increase, and if the temperature of the device increases, so then what will happen? Then the parameters of the device, different parameters, it can be current, voltage or any other parameters, those parameters value will also change. So then we will not get actual value of the static parameters. So that is why optimizing of this gate to source voltage is very important for this static characterization. So once we are applying this gate to source voltage, after that we will be able to find out drain to source voltage of the device, and similarly we will be able to find out drain current of the device. Okay, so now there will be delay between this gate to source voltage and the drain to source voltage, because this delay you can see here. So this delay, it is actually shown in this particular section. So let me select different color, so then it will be easier to see. So this portion you can see here, so the gate to source voltage we are applying here, and the drain to source voltage, it can be seen after a delay point. So this delay is very important. You know why it is important? Because by keeping delay we can allow the device resonant parameter, means if the device is turning on and in hard switching mode, so then what will happen? Due to presence of different parameters like capacitors, inductors, the parasitic parameters, there can be some oscillation during the starting. Similarly, during the turn off condition also this oscillation can present. If the oscillation is present, so then what will happen? That can cause some problem with respect to measurement of the static parameter. So that is why this delay is provided, so the device turn on and turn off happen such a way so that there cannot be resonant oscillation present in the static parameter characterization. So this delay, optimization of this delay is very important. So this delay we need to provide so that the device can reach to steady state within this duration. After providing delay, it may not happen that device is not reaching to steady state. It should reach to steady state and we can measure different static parameter. So this is the first thing which we need to consider, the static characterization. Second thing is the junction capacitance characterization. So junction capacitance this capacitances you know in terms of CISs, input capacitances, COSs, output capacitances, and then CRSs, reverse transfer capacitance of the device. So when I say input capacitances, so basically this input capacitor is having two different capacitor component of the device. So when you try to characterize the capacitances, the capacitance which we get to see in the device, that will be either gate to source capacitance, drain to source capacitance, or gate to drain capacitance of the device. Now these capacitances are actually give the value of this input, output and reverse transfer capacitance. So input capacitance will have two capacitances of the gate, then output capacitance will have two capacitances of the drain, and the reverse capacitance will have only one capacitance between drain to source. Now these capacitances are very important for designing any converter. As I have shown you in the last class, these capacitances are the main component which decides what will be the switching frequency of particular converter. Because you know, charging and discharging of these capacitances give us rise time and fall time, and that can give us actual value of the switching frequency. If these capacitances values are very high, then device operation will be limited to low frequency. That is what I have shown you in the last class. Silicon devices are generally having higher value of this parasitic or the junction capacitances, and it will be below, actually higher than that of the silicon carbide and GaN, and silicon carbide will be having higher capacitance than that of the GaN device. So since the GaN is having much lower capacitance, much lower junction capacitance, that is why this device is suitable for high frequency operation. Now these capacitances are not linear, they are non-linear in nature, and different parameter of the converter can affect the value of these capacitances. Different parameters can be, let's say, voltage rating of the device. Let's say some converter probably we are operating at 100 volts, some we are probably 400, some at 1000 volts. The variation in the voltages can cause different value of the capacitance. And then variation in the current, the drain current, so that can also cause the change in the capacitance value, and also the temperature. So these parameters, so basically the static parameter and the temperature affects this junction capacitances. So that is why it is important to characterize these capacitances in order to find out exact value of the capacitance from the graph with respect to the particular application. So the datasheet what I have shown you in the last class, there some values are given with respect to these capacitances, but those values are applicable for by considering the electrical parameter that they are given with respect to that particular test. So some parameter, electrical parameters are given for the test. So those parameter if you are considering for your converter design, then if you are choosing those capacitance values, then it will be perfectly fine. But if your electrical parameters are changing, so then what you have to do, you have to see, so generally in silicon device datasheet, those capacitances curves will be given with respect to drain current or drain voltage or the temperature. So then you have to select the particular temperature, particular drain current and the drain voltage. So then you can choose the appropriate value of the junction capacitances, and then from there the frequency can be calculated. So those calculations we will see in details in the next lectures. So today I'm just telling you the basics of this characterization. So why we need characterization, and what are the different types of the characterization. So we will see in details in the future lectures. So this is about the junction capacitance. Now third point is the dynamic characteristics. So dynamic characteristics, when I say, so this gives us the information about different dynamic conditions. So what are the different dynamic conditions? So dynamic conditions means the device has not reached to steady state. So either the device is turning on or the turning off. So then if the device is turning on, so during the switch on condition, so during the switch on condition, so it will tell us about the delay time during the turning on, rise time, then what are the other things? Also it will tell us about the DIDT and the DVDT. Similarly, during the turning off condition, means the switch when it is turning off, so then also we can get all this information. So delay time will be there for turning off, then fall time, then DIDT and DVDT. Are these the only parameters which we can get from the dynamic characteristics? So there is another important thing which we can get from the dynamic characteristics. What is that? That is the reverse characteristics. So if there is any reverse operation in the device, so reverse characteristics we can get. what are the reverse characteristics or the reverse parameters? So basically, reverse recovery time, then reverse recovery current, and the reverse recovery charge. Those information we can also get from the dynamic characteristics. We'll see about these characteristics in details in the next class, and also I'll discuss about different measurement equipment which are available for this different characterization. This is all for today. Thank you. See you in the next class.